right, so last time we looked at an example that involved what ended up being a inverse trig integral, or the result was an inverse trig function. So we also developed some general forms that we could maybe use from time to time, or we can always kind of go back through the process that we did this last time. So we're going to do one more example here, and we're going to use kind of both techniques again. So I just want you to see a little bit of both here. So suppose I had the definite integral, what example did I want to do here, of 3 over 4x squared plus 16 dx. All right, so in a situation like this, again, you might think to yourself, oh, maybe I should do a u substitution first. But we would be left with a similar situation that happened last time, so I'm going to save us from going through that. But if you were to try it, it's not that it's a bad idea to try, but it would be a bit like what we saw up here with number 7 last time, and we end up getting to a problem that we have an x. Oh, let's just maybe jot it out real quickly, because that's a common thing. Someone might think, oh, maybe I should do 4x squared plus 16, and then their du gives them 8x dx. But then here's this problem. Even when this whole thing is u, sure, I could, divide, but I don't have an x dx up here. All I have is a dx, a 3 and a dx. So this x is the problem. So we would run into something similar as last time. All right, so let's just erase all that and kind of observe that this should remind us a little bit of being something like, let's just kind of say, okay, this reminds me. So if I was going to do this all kind of from scratch, let's say, and you definitely might have Calc 2 instructors that do that. So suppose I think to myself, this reminds me a bit of, maybe it's similar / somewhat like the integral of 1 over 1 plus x squared dx. That's our tan inverse. All right. But of course, the main issue here, I can always deal with the 4x squared, this region in here where the variable is, that's going to be dealt with a u sub. But the first kind of issue that we want to focus on is that we don't have the 1. And so in this situation, we would say, okay, the first thing that I need to get here is I am going to need, in this denominator, I need to have a 1 plus my square of something. All right, so in order to do that, we are just going to factor out that 16. So we are going to have our integral, definite integral, and it's now going to be 3 over, factoring out the 16. So we're going to end up having to put a 1/4 in here. So this is going to be 16 times 1/4. Yep, that's 4x squared. And then that gives me that all-important 1 that I wanted to have there, dx. Okay, now the 3/16 can be factored out in front. That's no problem. But now the next thing I need to realize is this is where I'm going to need my u substitution. So this region right in here, this is what's going to correspond to the inside of our 1 over 1 plus x squared, and that's where we're going to need a u substitution. So we're going to have, and I'm even just going to pull my 3/16 out in front here, create a little more space. All right, and now I have the integral of 1 over, and I'll even reverse the order of addition so it starts to look a little bit more like what we see up above here. And so I'm thinking about what function being squared is in the location of that x squared. And so this is my inside. So right here, I am seeing the inside start to emerge. All right, so that's going to be what I use to drive my decision here, to let u equal 1/2 x, and then that means my du is 1/2 dx, and of course multiplying both sides by 2, I would have that 2 du is equal to dx. All right, so what do we have here? We have the u is equal to that 1/2 dx, that was that inside. And then we had to isolate for the dx because that's the only other x factor up there. I didn't have any other function of x, I only had the dx. So dx is going to be 2 du. So let's look at what we would now have here as I write out my integral. So I'm now going to have, this is going to be, it's this 3/16 that's now going to be multiplied by that 2, and then the definite integral of 1 plus 1 over 1 plus u squared du. So again, where did everything come from here? This is my u, and then the 2 du, that was the replacement for the dx. So this is exactly, the 2 over the 16 reduces to a 3/8, and then I have this definite integral that's actually, we're right at the point that we can evaluate it. So we have the 3/8 in front as the constant multiple, and this is straightforward arctan, or tan inverse of u plus c. And so what we end up with here is this is replacing that u. This is equal to 3/8 tan inverse of 1/2 x plus c. So this is, I guess I would say, kind of doing it from scratch every time, and it doesn't use those formulas that I wrote out last time. It doesn't use those in any way. So this is the approach that would work every time. So get the 1 first in these situations, and then figure out, what your u needs to be. Now, if I wanted to take a slightly different approach, and again, depending on your instructor, you might see it done either way here. All right, so the other way is, let's say or here. Let's go back to this original. I'm going to factor the 3 out in front. So we're going to have 3 times my definite integral of 1 over 4x squared plus 16 dx. Now, even with these, I don't know, shorter, maybe slightly shortcut formulas, you see the one at the top there? It says it's for 1 over a squared. Okay, that could be fine. That could be my 16, but then just plus plain x squared. And so I don't have a plain x squared. So that was what my comment was last time. The inside is where the x is. And if that is more than just a plain old x, we need a u substitution on that. So we're going to still need a u substitution on that term right here. So let's go ahead and just kind of think about how we would rewrite this, because it's not just x squared. It is really the quantity of 2x that's being squared there. And then you could think of the 16 in terms of that a, the 16 is a 4. But this still requires, albeit a slightly maybe shorter u sub, this still requires a u sub. So we would start off and we would say, okay, let's let u equal that 2x. So this is my u. And then my du here, my du is just going to be 2 dx. And of course, dividing both sides by 2, we're going to have our 1/2 du is equal to the dx. So we isolate for our dx because that's the only x that's left and there's no other factors of x. So that 1/2 du. All right, so this is now going to tell me I would have, so this would give me the 3 that was there, the 1/2 that's coming from that du factor, and then the 1 over u squared plus 4 squared du. So this time, again, that was my, oops, highlighter please. This is my u, and then my 1/2 du, that's what replaced my dx. So now I need to scroll this down just enough so you can hopefully see at the top up there that our formula for this is going to be, kind of think of it from a formulaic approach. So this is going to equal, so first of all, we have the 3/2 in front that's getting carried along as a constant multiple. And now from that arctan formula, you would have 1 over a, and the a is 4 here. So this 4, that little 4, this is the a value. So we're going to have a 1 over 4, and then times my definite, I'm going to the result, sorry, times the result is the arctan, or the tan inverse of the u over, and again, it's u over a, and a in this case is 4. All right, so this looks a little different, but we haven't yet simplified it, and we haven't yet replaced our u yet either. So our last step, we'll kind of clean up our constants here, and then we are going to replace that u with, it was, what was u? U was 2x. So we would have our 3/8 tan inverse of 2x over 4. Well, of course, the 2 over 4 is going to reduce here, and so we do get to the same result, the 3/8 tan inverse of x over 2 plus c. Okay, so it's two different approaches, but notice they both require u substitution. Again, some instructors might prefer one over the other, so I'm just kind of showing you both. All right, so the last little topic I'm going to introduce in this video is going to be definite integrals and how that works with u substitution. And we're going to have two different methods. Again, you may see one instructor tend to gravitate towards one more than the other as you go on to Calc 2. And so method 1 may be the most intuitive one, kind of what I would have guessed some of you would have done even if I didn't tell you what to do. So we're going to start with that one. All right, so suppose that I have the definite integral from 1 to 4 of the square root of 1 plus the square root of x all over the square root of x dx. It's a lot of square root of x's. All right, so we're going to start off and say, okay, I want to, first find what the value of this antiderivative is. I want to integrate. And so it looks like I have a kind of a common inside thing happening here, something inside of a radical or an outer power. So that's where we're going to start on this. So we're going to let our u equal 1 plus that root x. And that, of course, means that du, that's x to the 1/2, so that's going to be 1/2 x to the negative 1/2 dx. Or, if you prefer, we could say that is the same thing, of course, as 1/2 times 1 over the square root of x, or 1 over 2 root x dx. And so this actually looks pretty good because the portions that are x's and dx's that are left in the original integral here is a dx over x. And guess what? That's exactly what I have here. I just need to multiply both sides here by this 2 in order to isolate for that 1 over root x dx. So now I'm going to have my 2 du equals my 1 over root x dx. All right, so here's where we're at. So there's my 2 du equals the 1 over root x dx. All right, so let's see kind of where this would take us in terms of our integral. It looks like I'm going to have a square root of my u. Well, u, of course, that's what I'm subbing. And then the dx over root x, that is being replaced by the 2 times the du. So that's the replacement for the 1 over root x dx. Now, here's the thing. This is now an integral that is in terms of u. It would not make any sense to put a 1 and a 4 here because these are really x limits of integration. These were related to the original x integral, excuse me. So those are really x limits of integration, even though we don't often write it that way. That's really what those are. Those are x values. That looks kind of weird to see that there, so I'm just going to erase that, but those are really x's. So it wouldn't make sense to put a 1 and a 4 here. So I'm just going to put little boxes for right now, just to be mindful that I do have a definite integral that eventually I am going to need to get back to. All right, so I have my 2 and this definite integral of u to the 1/2 du. That, of course, we do know how to integrate. So add 1 and divide by it. So u to the 3/2 divided by 3/2. And of course, hopefully you're at the point where you're just right away saying, oh yeah, that's like multiplying by 2/3. Okay, but this time I'm not going to put in a plus c because this is not an indefinite integral. It's going to be a definite integral. So I'm going to have numbers to sub in. Okay, but I need to keep going here, so think about what you would do if it was an indefinite integral. You would keep going, and this is method 1, where you would go back to the x's, and you'd say, okay, I'm going to replace my u with that 1 plus the square root of x, and so that's what it would be if it was an indefinite integral, except of course you would just tack on a plus c. So the first method is to take it all the way to the end, just like you normally would. And instead of saying plus c, once you go back to the x's, now you can evaluate between your x limits of integration. And so now you would sub in your 4. So 4/3, 1 plus root 4 there, of course, is 2. 1 plus 2 is going to be 3. So I would have 3 to the 3/2. And then minus 4/3, which again could be factored out if you would prefer, times the quantity of 1 plus root 1. Root 1, of course, is 1, and 1 plus 1 would be 2. So 2 to the 3/2. And so this is, my final result here. You could factor out the 4/3 if you want to. We could maybe do more with that, but it's like a square root cubed. So, I'll just leave it as 3 to the 3/2 minus 2 to the 3/2. And then if we were so inclined to go to a decimal, I have this jotted down from earlier. It's approximately 3.157. So this is the exact and an approximate value of this definite integral. So this example right here that we just did, so this one was with method 1. So number 1, we just evaluated here. I'm going to put this up above here. This was with, so number 1 that I did is with method 1. So method 1 essentially says, treat it like you would if you were doing the indefinite integral, and go back to x's and then just sub in between your limits of integration. So you go all the way back to x's, you get down here in terms of your x's, and you sub in the 4 and the 1. So that's method 1. Okay, and I'm okay with that. But there are other instructors that might prefer method 2. So we're going to do another example here, and this time we're going to do the other method for a definite integral. So this is going to be a different example, just so we're doing different types of problems along the way. So still honing in on U substitution, right? That's a big deal. So this time we're going to do a definite integral with method 2. Okay, so method 2. Method 2 says instead of going all the way back to x's, you're going to stay in terms of u, but you're going to convert those x limits of integration into u limits of integration. All right, so let's say on this number 2, so here's number 2. Let's do the definite integral from 1 to 2 of the natural log of x over 2x dx. So first of all, kind of as we're working on these, realize that anytime you're doing a definite integral here, you need to be defined continuous from the interval from 1 to 2. This was x equals 0, does not exist in the integrand, so I had to be careful as I'm writing this problem that I didn't go from 0 to 2 or -1 to 2. But we're okay here. All right, so as we look at this one, this is a new type of u sub that we haven't seen before. So here's the comment I want to make. If I even gave you just the integral of natural log of x, you would not yet know that one. We have never learned a function. If I ask you to think of some function whose derivative is natural log of x, we haven't learned that. We don't know the antiderivative of the natural log of x. And so what that's going to mean in terms of our u substitution ideas is that if you have a natural log of x kind of anywhere inside of your integrals, oops, I didn't mean to erase that. That is going to be what we are going to use for our choice for u. Because I need to get rid of it, because if it's in there, I can't take its antiderivative. I need to get rid of the whole natural log function, no matter where it is. And so that's going to be our first step here, is letting u equal that natural log of x. All right, so my differential here is going to be du is 1 over x dx. So this is my du, my 1 over x dx. And this is looking great because I actually have here a dx over x, a 1 over x dx. So this looks kind of perfect here. Looks like I lost my 2 there. Okay, so as we go to our new integral, this extra 2 in the denominator, that's really no problem. So we can even bring that little guy, all the way out in front. So we can just bring this as a 1/2 multiple out in front. And then I have my u, that's that natural log of x, just sitting right there, fine, in the numerator. And then the dx over x, that's my du. So there's my dx over x. All right, so there's where I'm at. And now, instead of just putting boxes here and waiting until we go all the way back until the x's, we can actually, I can't put 1 and 2 in there, definitely not. But what I can do is I can change those x limits of integration into u limits of integration using my choice of u. I said that u was going to equal the natural log of x. The lower limit as an x limit is natural log of 1, and natural log of 1 is 0. So I'm going to now have my lower limit, and so this is a u limit is 0. And again, here I can say u is equal to the natural log of 2. So that is going to be my u limit of integration. So this is the other option. It says we can, in addition to translating everything in terms of the integrand into u's and du's, why not also just change the limits of integration into u's? So then, if we do that, we never need to go back to x's. So now I'm going to have 1/2. The integral of u is going to be u squared over 2. There's no plus c because we have a definite integral. And in this case, I have already converted those into my u limits of integration. So these are u limits of integration. And so that means I can go right to evaluating in between these limits. So I have the 1/4, and then in for u, natural log of 2, quantity squared, minus 1/4, and then in for u, 0 squared. So my final answer here is going to be 1/4 the natural log of 2 quantity squared. And so that is our final answer. So this is method 2. So method 1 makes you go back to x's and use those original x limits of integration. So here we went back to the x's and we then use the original x limits of integration. So that's what we start with in the original integral. These, again, these are really, they correspond to the same original variable. They're x limits of integration. Method 2 says you don't need to do that if you convert these into your u limits of integration. And so that's what we did on this one. So those are the two main techniques for doing definite integrals with u substitution. So we'll probably do one more video when we come back, maybe just another couple of examples to sort of wrap up this all-important u substitution section.